So question 5.2 defines a weakly deterministic context-free language if it's accepted by a DPDA via empty stack, and it's deterministic context-free if it's accepted by a DPDA via final state. So we have to show all weakly deterministic context-free languages are deterministic context-free languages, and all deterministic context-free languages are context-free languages. Well, we know that all WDCFLs are DCFLs because the property of being accepted by empty state is weaker than the property of being accepted by final state. That was what the previous question proved, right? So that gives us that these class of language here is a strict subset of deterministic context-free. And we know that deterministic context-free languages are a subclass of context-free languages because every DPDA, that is deterministic push-down automator, is just a special case of push-down automators, right? The transition function just has more restrictions on it. So we basically get this as a subclass of that for free. So that's the easy part. The hard part is showing that these inclusions are strict. So we have to find some language L1 that is deterministically context-free, but not weakly deterministic context-free. And that's pretty easy to show because we know that all weakly deterministic context-free languages have to satisfy the prefix-free property. So I can just choose some language that I know doesn't satisfy the prefix-free property, say the language of 0 and 00. It's pretty clear that this language is going to be deterministic context-free because, I mean, it's regular, right? I can just build a state machine that just checks if the string is either this string or that string, and it doesn't even touch the stack, right? And because all DFAs are just like a special case of deterministic push-down automators, this language here must be DCFL, but because it's not prefix-free, it can't possibly be weakly deterministic context-free. A harder property to show is a language that's context-free but not deterministically context-free. I won't go into the full details of the proof of this one, but I'll just give the intuition. So if we choose L2 to be all strings of the form W, W reversed for some string W, then this language will be context-free because I know I can generate a grammar for it. We did that back in exercise 1. But it can't be deterministically context-free, and the reason being is, suppose you try to design a deterministic PDA for this language here. The problem is you'll try to push the W onto the stack and then pop its reverse off to match it. You won't know where the middle part is ahead of time. You won't know when to stop pushing stuff and start popping stuff off. The DPDA will have to magically guess where the midway point is, and it can't do that because it's deterministic. A more concrete counterexample, if we take these two strings, both of which are clearly in L2, because they both start with the same prefix, the DPDA has to do the same things, right? Because it's deterministic. So if it wants to match X, it's going to push these three characters on the stack, and then it's going to try to pop these off afterwards and match them, right? So this matches that, this matches that, this matches that. Aha, this is in the language. And it can't know ahead of time how long the string is, so it's going to have to do the same thing. It pushes these three characters, and then matches and pops the one. It matches and pops the one. Oh, hey, this character doesn't match, therefore Y can't be in the language. But Y is in the language, right? So no matter how we try and design it, DPDAs will always fail to recognize this language. So this is a language that's CFL but not DCFL.